In this lecture, I'll review the recent significant entropy-related concepts we've been covering in the last few lectures in order to help reinforce this material. I'd also like to point out that at the end of this posted lecture notes are 11 worked out examples. You should take a look at those. I highly recommend you look through all of the problems and then try to do a few of them on your own without looking at the solutions so that you can test how well you can apply the entropy tools we've been developing. As always, if there's any material you don't understand, please let me know via Piazza as a private post, for example, and I'll do my best to respond quickly. Okay, this is lecture 26. In this lecture, we're going to review some of the recent materials related to entropy and the entropy equation, and then we'll have some examples. Okay. So let's get started. First of all, let's focus on the maximum performance measures for cycles that we've discussed previously. So that's this first bullet point. These have to do with the power cycle. That's the first sub-bullet there. So the thermal efficiency for a power cycle. The second sub-bullet is the coefficient of performance for a refrigeration cycle. And the third sub-bullet is the coefficient of performance for a heat pump cycle. These are all the maximum performance measures, meaning that they're for internally reversible processes. So it's very important. I'm going to highlight that on each one of these because the expressions here are only valid for internally reversible cycles, and that's the maximum that you can possibly have. Any real cycle will have an efficiency or a coefficient of performance less than this. These maximum performance measures are all based on the absolute temperatures of the cold and hot reservoirs. So if you look over on the right-hand side, this first schematic here is for a power cycle. You see that we have a hot reservoir at an absolute temperature of TH. Remember, these are absolute temperatures. They're not degrees Celsius or degrees Fahrenheit. Instead, they're Kelvin or degrees Rankine. So we have a hot reservoir. We get heat from that hot reservoir. That's the QH. Goes into our system. And again, the system consists of a number of components. For example, in a power cycle, you'd have like a boiler, a turbine, a condenser, and then a pump. And that's all contained within this system. And then we offload some heat through the condenser, for example, to the cold reservoir, which is at an absolute temperature of Tc. And then we get some net power out of this, which we call W by. So that's the net power coming out. And the maximum thermal efficiency that you can get out of this kind of power cycle will be 1 minus the absolute temperature of the cold reservoir divided by the absolute temperature of the hot reservoir. Similarly, we have the coefficient of performance for a refrigeration or heat pump cycle. That corresponds to the picture on the right-hand side here, the one that I'm now circling. Picture looks very much the same. We have the cold reservoir and the hot reservoir at their absolute temperatures. Again, the system consists of all the components that you might find in a refrigeration or a heat pump cycle, like a compressor, a throttling valve, etc., all those kinds of things. We have to put some work into that in order to move the heat from the cold reservoir to the hot reservoir. For a refrigeration cycle, what we're most interested in is how much QC we can move divided by the amount of work that you put into it. And for a heat pump cycle, it's how much heat we can move into the hot reservoir compared to how much work you have to put into the cycle. So again, the maximum performance measures for these, for the refrigeration cycle, it would be the temperature of the cold reservoir divided by TH minus TC. And for the heat pump maximum performance measure, it would be the temperature of the hot reservoir divided by TH minus TC. So these expressions here give you the maximum that you can possibly obtain given any power cycle or refrigeration or heat pump cycle. They're useful to know because like I said before, any real cycle will have a performance that's less than this. So it gives you an idea of what's the maximum possible that you can achieve and how close, and then you plug in the numbers for your real situation and just see how close you are. And again, it's very important that you use absolute temperatures in these calculations. Okay, let's move on to the next topic. The next one is the property of entropy. So we have specific entropy, little s. It's a property so it doesn't matter on what kind of path you use when you compare values between different states. The definition for a small change in entropy, ds, it was defined as the heat going into your system divided by the absolute temperature where that heat is being put into the system. So that's the absolute temperature where the heat is going in, and then you add that up over the entire boundary. That's the integral sub b here. That just means that perhaps you have, let me just sketch this out. Let's say this is your system. Perhaps you have heat coming in different locations. You just want to make sure that you're using the temperature, absolute temperature at each of those places where the heat's coming in. Right, so you want to add that up over the whole boundary. Again, that's the integral sub b there. And specifically, this kind of process for the definition of entropy has to occur in an internally reversible manner. Okay, so that's how entropy is defined. And just from that definition, if you do some rearranging of that expression, let me just do a quick rearrangement of just one particular place where heat's coming in. So just rearranging that equation to write it as dq equals t ds. If you look at that for a moment, if you plot this on a TS diagram, so that's the plot that's right below the expression there, you see a TS diagram, the heat that would be coming into your system as you go from state 1 to state 2, as shown in the diagram here, would be equal to the area underneath that curve. That's the T times ds. ds would be just a small displacement along the horizontal axis, and T gives you the height, so it's a small area here. And then when you integrate over the whole path from state 1 to state 2, you get the total heat going into your system for an internally reversible process. If it's not, if it has some irreversibility to it, then it will be different than what we have here. Then what happens is entropy production, that sigma quantity, comes into play. So the area under the curve is only the heat that would go into your system for an internally reversible process. I want to really emphasize that this is only true for an internally reversible process. The area under the curve does not hold if it's irreversible. By the way, while I'm on the plot here, I should just point out these TS diagrams we're going to use very frequently. They look very similar to TV diagrams, at least in our sketches here. In a real plot, when everything's proportional, they do look different, but as a sketch, they look similar. We still have the vapor dome, looks much the same as it was in a TV diagram, and then we also have isobars that look much the same as what they did in the TV plot. So here's one isobar, here's another one, and as you go this direction, the isobars, the pressure increases. Okay, and then the path I have here from 1 to 2 is just some arbitrary path. I just wanted to show that the heat for an internally reversible process is equal to the area underneath that curve. Okay, so how do we find the entropy for various substances? Well, we always have the tables that we can turn to, so I took a little snippet from one of your Excel tables. This one I believe was for water. And you have already seen that there is a column here for the specific entropy for a saturated liquid and a specific entropy column for a saturated vapor. So if you're dealing with a saturated liquid vapor mixture, we can always go back to our standard way of calculating property, where the specific entropy would be 1 minus the quality times the saturated liquid value for the specific entropy, and then you add in the quality times the saturated vapor value for the specific entropy. So that's how you would calculate the specific entropy for a saturated liquid vapor mixture. For superheated vapor, you can look straight at the superheated vapor tables, and there'll be a value for entropy there, so you can just look it up directly. For compressed liquids, the tables are too coarse to use in practice, so we instead use the approximation that I give in this first bullet, that the specific entropy for a compressed liquid at any temperature and pressure is about equal to the specific entropy for the saturated liquid at the same temperature. So this is much the same as how we found the specific volume and the specific internal energy for compressed liquids. So that's how you would look up the value for entropy in a table, or specific entropy in a table. We also have the TDS equations given in the last bullet point here. These we discussed in the last lecture. These are expressions just that give us a way to relate properties to one another. And there are two TDS equations. The first one is TDS equals du plus PdV. So it involves the specific internal energy. And then the other one involves the specific entropy. Specific enthalpy. So TDS equals dH minus V dP. So they're just two TDS equations we can use to relate properties. So it's just a handy way to convert between various properties. All right, let's move on to the next thing. We'll talk about the entropy equation. This one looks a little different than what we've talked about before, because what I've done is I've written down the control volume form of the entropy equation. So that's our first bullet point here. On the left-hand side, we have ds dt. This is the time rate of change of entropy inside our control volume. So let's say we have some control volume here. The time rate of change of entropy on the inside of the control volume is this yellow term, ds dt. So that's how ds dt is how the entropy of the yellow stuff is changing with respect to time. And with our control volume, it's possible you have some flows of materials coming in and out of the control volume that bring in their own entropy and then take out some of their entropy. So, for example, here there may be some mass flow rate coming in, and it has some entropy coming in. We'll just call that in. So we bring in some entropy into the control volume, and then maybe we take some entropy out through the outlets. So that's what these terms are that I'll highlight in orange. So we've got the entropy coming in here, and then we have the entropy going out over there. So there may be multiple inlets, multiple outlets. Then we also have, and I'll do this in blue, there may be some heat coming into our control volume. And this is actually the rate at which heat is coming in, Q dot into. And so that's our third term on the right-hand side. This is the rate at which energy is coming in via heat transfer, divided by the absolute temperature where that heat transfer is crossing the boundary. And then we add up over the whole boundary. So there may be multiple places where that occurs. So we would need to account for that. So we would, let me put some numbers on this. So this would be maybe location 1, here's location 2, for example, and so on. And then lastly, if the process is internally irreversible, then we have those, we have to include that entropy generation here as well. So sigma dot here is the rate at which we're generating entropy. So it looks a little different than what we've talked about before, because we've added these mass flux terms where you have some mass that can come in and some mass that can go out. If you're dealing with a closed system, then the incoming and outcoming terms just go to 0 and you get back a previous expression that we've looked at. If you take that expression and you integrate it in time, then what happens is the ds dt term becomes a delta s. The m dot term just becomes the mass in. The m dot out term just is mass out. Q dot term is just the heat in. And then the rate of entropy generation just becomes the entropy generation. And by the way, I should just point out that the sigma, it goes by two names. It's either called entropy production or entropy generation. You'll hear both. It's not the entropy, but it's a different quantity in and of itself. It has the same units as entropy, but it's not entropy. S is entropy. Sigma is entropy generation or entropy production. They're different quantities. The entropy production, entropy generation term, that's the term that starts to account for irreversibilities, right? Because the sigma or sigma dot term is equal to 0 if you're dealing with an internally reversible process, so it would be equal to 0 if you're dealing with an internally reversible process. and then in that case, and that corresponds to just the entropy S term, right? If you go back up to our definition for entropy up here, you can see that corresponds to internally reversible process. But if you're dealing with an irreversible process, then you start to deal with the greater than sign, and that's when you have some entropy production that's occurring. All right, let's continue on. If it is so I should point out that the change in entropy for a control volume or system can be less than 0. That a lot of people don't realize that, but you can have a reduction in entropy. It's no problem. What that means is that there must be heat transfer going out of your system, that the dq over T term has to be less than 0, which means that there has to be heat transfer out of the control volume. So don't be alarmed if you see a change in entropy that's negative. It's not a problem. It just means that heat transfer is going out rather than in. The thing that can't be negative is the entropy production, sigma. That one must always be positive or equal to 0. The entropy itself can be positive, negative, or 0. Okay, the only thing that we have a restriction on is the entropy production. Okay, the next bullet point. For a closed system or an open system where the mass coming in and the mass going out are the same, okay, if you have that kind of a system and then the processes that you're involved with are adiabatic, so the Q term goes to 0, and internally reversible, so that the entropy production term goes to 0, under those conditions, you will have an isentropic process where the entropy does not change with time. So, for example, here ds over dt would be 0, or delta S would be 0. Right? So if you just go back up to our entropy equation, I'm going to go ahead and erase a few things. I'll just deal with the second version of it. If there's a closed system or the mass coming in equals the mass going out, the term I just circled there would be 0. If it's adiabatic, then that term that I've just circled is 0. And if it's internally reversible, the last term is 0, and so delta S would have to be 0 for that case, meaning that it's isentropic. Now the opposite is not true, and I've talked about this before. If you have an isentropic process, it does not imply that you must have an adiabatic and internally reversible process. It's possible, although very unlikely, that you could have a negative heat transfer term, so heat's going out of your control volume, and a positive entropy generation term, right, so that it's internally irreversible, and it just so happens that those two add up together to cancel out one another and give you with an isentropic process. So just because it's isentropic, it doesn't necessarily mean that it has to be adiabatic and internally reversible. It often is, because it's a special case that the two will add together and cancel one another out. So it's unusual, but it's not impossible. So just be aware of that adiabatic and reversible means isentropic, but isentropic does not necessarily mean adiabatic and reversible. Okay. Again, these are all review items. I've talked about all these things in previous lectures, but I just want to go through them again for you here so that they're cemented in your mind a little better. Okay, now with the rest of the review, I'll talk about how we find the change in entropy for our various models. So, for example, the incompressible substance model and the ideal gas model. So we've already talked about how to find the entropy from the table, like the superheated vapor table, saturated liquid vapor mixture, or use the compressed liquid approximations. But now let's just say we want to use a model instead of the tables. So for the incompressible substance model, I've put a review of all the various things we've learned about that model. So, for example, that you'd be dealing with, so liquids and solids are often assumed as being incompressible. If you're dealing with something that's incompressible, the specific volume remains constant. You have one specific heat, we'll call it C. It's just a function solely of temperature. You can show that the specific internal energy is a function only of temperature. The specific enthalpy is a function of temperature and pressure, so two properties. And the specific entropy is a function only of temperature. So the specific entropy is the new one here. Define the change in the internal energy. Specific internal energy, it's just the specific heat times dt. And again, the specific heat in general is a function of temperature. If you integrate both sides there, you'll get the delta U is equal to the integral of c dt. For the specific enthalpy, we can just make use of the definition of the specific enthalpy. So H equals U plus PV. And then we take the derivative of that whole equation. Oops, I made a mistake there. If you take a derivative of the whole equation, what you end up with is dH is equal to du plus pdv plus vdp. But the pdv term is 0 for an incompressible substance, and so then what you're left with is dH is equal to du plus vdp. And then again, if you integrate both sides, you get delta H is equal to delta U plus delta P times V. And then the last one, which is the new one dealing with entropy, ds is equal to the specific heat times dt over T. And you'll see that the whole right-hand side is really just a function of temperature. So when you integrate both sides there, you get delta S equals the integral of C dt over T. And again, in general, the specific heat's a function of temperature, so you would have to actually evaluate that integral. If, however, the temperature range isn't too large, and we can assume that the specific heat is constant, then we can pull the C outside all of those integrals, and it makes everything a little easier. So the delta U just becomes C delta T. Delta H becomes C delta T, because that's the delta U part, plus delta PV. And then the change in entropy, the delta S, is C natural log T2 over T1. And again, it's very important you use absolute temperatures when you evaluate these ratios, because it won't work if you use degrees Celsius. So that's the incompressible substance model. For the ideal gas model, I'll just review everything we have here. We have the ideal gas law, so everyone's familiar with that, so I won't go through that in any detail. We have a couple of supporting relations that come from some minor derivations. So the specific heat at constant pressure, Cp, is equal to Cv plus R, and the specific heat ratio is Cp over Cv. In general, the specific heat at constant volume is a function of temperature, and the same thing for specific heat at constant pressure, Cp. It's a function of temperature. In the ideal gas model, the specific internal energy is a function of temperature, and the specific enthalpy is a function of temperature. And the specific entropy is a function of temperature and pressure. The change in the specific internal energy is Cv dt. And again, you can integrate both sides to get delta U is equal to the integral Cv dt. Again, Cv is generally a function of temperature, so you'd have to account for that. Fortunately, the ideal gas tables, and you can see this at the very bottom here, in the yellow table, that integral has already been performed for you from some reference condition to whatever temperature you're interested in. So, for example, here's the column dealing with the specific internal energy at any given temperature. The change in specific enthalpy is Cp dt, so you can do the integral for that. And again, in general, Cp is a function of temperatures, so you'd have to account for that, but the ideal gas tables take that into account, and you can see that column in the ideal gas table. The change in entropy is more complex. So ds, there are two ways you can write this. One is Cp times dt over T minus R dp over P, or ds is Cv dt over T plus R dv over V. Just two different ways that you can arrive at that, two different expressions you can derive there. If you integrate the one involving the pressure, then you end up with the next bullet point. So delta S is delta S naught minus R natural log P2 over P1. The S naught terms are they're functions just of temperature, and again, those are summarized in the ideal gas table. So that's this very last, or not the last column, but the third column over the S naught values. And again, what the S naught term is it's the integral of it's the integral of, let me just write it over here, S naught is, at some temperature, is the integral from some reference temperature to some final temperature of Cp T dt over T. So that's what's being tabulated and put into the tables, just so you don't have to do that integral. Okay, if the process is isentropic, so that S2 equals S1, then you can rearrange the previous equations. So the one that I'm underlining right now just comes from the very last bullet point right above it. The next two actually come from the those actually come from these equations up there, the ds, and it's function. They're two different equations there. So if you set ds is equal to 0, and then you do that some rearranging and define PR and VR, you can get these ratios. So the P2 over P1 is equal to PR at T2 and over PR at T1. Where the PR has been pre-tabulated, again, it's a definition for quantity. I'm not going to review it here, but it's in the last set of notes, or that last lecture notes. But the PR is given in the table, same sort of thing with the VR. It's just very handy to have these things tabulated, so it gives you a quick way to find pressure and specific volume ratios. And again, those things are only functions of temperature. So the PR and VR quantities in the tables can only be used when you're dealing with an ideal gas and an isentropic process. So be aware of that. In fact, I'm going to circle it here and just make a note of ideal gas plus isentropic. Okay, that's what's required to use those. And just like with the incompressible substance model, sometimes we deal with temperature ranges that aren't too large, and so we can assume that the specific heats are constants. They're not the same constant, they're just different constants. But if we can do that, then we have what's known as a perfect gas assumption. Then our previous equations, we don't have to worry about doing the integral. It's, for example, the du one, so the change in the specific internal energy, the CV could come straight outside the integral there, for example. So you would have delta U is equal to CV delta T, delta H is equal to Cp delta T. You've seen these sorts of things before. But now the ds equation, so this is the one that I'm going to highlight right here, you can integrate that on both sides, assuming Cp and Cv and R are all constants. And then you get these two expressions here. And again, if you're dealing with a process that's isentropic, such that S2 is equal to S1, then you can take these two equations and rewrite them so that you get convenient relations relating the specific volume ratios, temperature ratios, and pressure ratios. And they're all in terms of the specific heat ratio K. Remember that K is Cp over Cv. Okay, I think that's all I wanted to show you for the review here. Again, this is all review. We've talked about all these various things previously. I just wanted to have it all in one place for you in the notes, so you have a chance to review it and a convenient place to come back and refer to it should you need to.